Okay, welcome everybody. Not really. We'll teach us both late today.
I picked a good day to be late then.
Yes. All right, so I have to apologize for not posting homework 7 until last night. I thought I'd uploaded it, but James let me know that he was getting started early and it wasn't there yet. He straightened me out, so it's there now. It's due on Wednesday, channel geometry. Also a reminder that you should be working on phase 1 of the project. The demand estimation is due a week, Monday, March 9th. That doesn't work, does it? 9th? Yeah, that works. Okay. I was thinking the numbers didn't add up, but they do. So the design project is due the first phase on Monday, and that's where what you're doing is you're figuring out how many people are going to be in each of the zones, how much water demand is there per person, and working through that summary sheet that I've given you to identify the average flow, the peak day flow, the peak hour flow, and then combining it all together. So as you work on that, let me know if you have questions, and I'll be happy to explain the structure of that summary form, or look over any data that you found, sort of anything that you want to ask me about. Feel free to stop by during my office hours or send me an email, and I'll be glad to go over it with you. All right, so what we're going to do now is move on from Chapter 10 and into Chapter 11, where we're learning about how to calculate what is the flow depth when conditions are steady and uniform. And so Manning's equation is the formula that we use for steady uniform flow, and that's what we'll be talking about today. Before we get into it, are there any questions related to the announcements? All right. The most common geometry for flow in open channels is trapezoidal geometry. And in table 10.1, you can look up the geometric parameters for the cross-sectional area, wetted perimeter, hydraulic radius, and so on. And so just to get some experience with these hydraulic parameters, I'd like for us to take a look at this trapezoidal channel where the bottom width is 15 meters, the top width is 35 meters, and then the side slope is defined in terms of how many units of horizontal length are there for every unit of vertical distance. And so with t equals 2, what that means is for every y, every meter of depth, then this segment on the side, the length would be 2 meters. And there's, of course, since it's trapezoidal on both sides, then what that means is that capital B, the top width, is b, the lowercase, the bottom width, plus 2 times the distance that we calculate on the top of that side triangle. So let's go through this. What would be the depth, the area, wetted perimeter, and you're going to be able to get the depth from the fact that we know the top width and the bottom width both. And so you're going to break up this top width into the pieces that's directly above the bottom, and then how much distance is there to the right side of that inflection point, and so on. So let me pause for a moment and give you a chance to start calculating on this, and then I'll bring it up on the screen to see if we're all getting the same numbers. Okay, just to jump ahead a little bit, I want to point out that what we know is that the top of this triangle on the side, excuse me, is going to have a distance of 10 meters because the total length of the top is 35. 15 of that is directly above the bottom of the channel, and so that means that there's going to be 20 meters that's not directly above the channel, so that would be 10 on each side. And so the question is if we have 10 as the top width of that triangle, and we know that the side slope is 2 units of width for every 1 unit of vertical, because t equals 2. So back to this, this explanation that we have in this sketch, it's 1 to t. And so we know that, from like triangles, that t2 is to 10 as the unknown height y is to 5. And so therefore we can find that y is 5 because it's the same, 10 is to 2 as the height y is the vertical component. So that gives us the depth of flow. And if we know now the depth of flow, all of the other parameters like the area, wetted perimeter, hydraulic radius are dependent on the depth. So let me I'll pause for a little bit longer this time, calculate the wetted perimeter, hydraulic radius, and hydraulic depth D. So the wetted perimeter is a physical measurement, and the wetted perimeter is talking about the distance starting here at the water line and following down at all of the portions of the channel where water is in contact. And so the wetted perimeter is going to be the 15 meters of this bottom length and then the distance of the 2 side slopes. So in order to calculate the wetted perimeter, you'll notice that we have this factor W that takes into account the angle of the side slopes, because that angle is going to affect the overall wetted perimeter depending on if it's vertical, then it's relatively easy to find the wetted perimeter. If it's a rectangular channel, then the wetted perimeter is simply the depth of flow on either side plus the bottom width. But as the channel lays down and as the T value increases, then the wetted perimeter is going to go up as well. And W takes that into account. So what we should get is a wetted perimeter of 37.36 meters. And then the hydraulic radius is the ratio of the area to the wetted perimeter. And then the hydraulic depth, this term D, is essentially the equivalent depth as if the channel was rectangular. So any questions about that?
What do you use hydraulic depth for? I'm not sure what that is.
Well, if you look at the actual depth in this example, it was 5 meters. So the hydraulic depth is telling you if you had an equivalent channel that was rectangular rather than trapezoidal, what would that depth need to be in order to achieve the similar flow characteristics?
Oh, okay.
So it's kind of it's a way of expressing this trapezoidal channel in terms of an equivalent rectangular channel. You'll remember that in class on Friday, I think it was, we looked at this force balance for an element of water, and we said that there was the weight of the water acting downward, there was the hydrostatic forces pushing this element to the right, other hydrostatic forces pushing to the left, and then there was also the flow resistance force that was as a result of the shear stress moving in the opposite direction of the flow. This was for a channel where the water surface was decreasing. So these conditions weren't steady and uniform. The situation is considerably more simple if we assume that the flow is steady and uniform. And so here is a similar cross-section, but instead this time we have the bottom of the channel, and you'll notice here the slope of the channel, S0, is parallel to the slope of the water. And that slope is also parallel to the slope of the energy grade line. And our book sometimes, instead of calling it the energy grade line, which you're already acquainted with, they call it the total energy line. It means the same thing. It means the flow depth plus the velocity head. And so this little triangle, and the WS stands for water surface, and so the triangle is identifying the physical location of the free surface that's in contact with the air. And these little marks that are underneath the triangle, likewise, they're meant to indicate like the shimmering or like the ripples on the water that you'd see if the water was in contact with the atmosphere. So this is the water surface, and above the water surface, some distance equivalent to the velocity head is the total energy grade line. Now, the slope of the energy grade line is related to the shear stress, and this is a formula that you've seen before relating shear stress and the slope of the energy grade line. But the question is that we're trying to find out with Manning's equation is what's the depth of flow? So if we have a certain slope, how deep is the water going to be for a flow rate that's given? Or if we know the depth and we know the shape of the cross section, then what's the equivalent flow rate that's causing that? So the normal depth, as this is called, only applies if conditions are steady and uniform. And Manning's equation, which we're going to be using today, only applies under these circumstances. But if we break a channel up into small pieces, if the conditions are non-uniform, we can look in smaller segments of a river, for example, and apply Manning's equation. Because a river is an example of a non-prismatic channel where maybe it's going through lots of different bends and it has an irregular profile, but if we break it up into smaller pieces, we can find within those small pieces uniform flow. So that's what Manning's equation is assuming. And if you look at this figure, the energy loss that you're losing as the water is flowing downstream, there's a delta Z, is the energy loss, because the slope of the energy grade line and the slope of the channel are parallel, then the head losses and the delta Z is equal. So this is the flow energy equilibrium, is just that the energy loss is equal to the elevation change. And so here you can see the H sub F between two locations. Location 1 is here where we have this first delta Z indicated, and so the total energy at this upstream location is the elevation difference above a datum, the depth of flow, and the velocity head. And so that's how much energy there is at 1. And now at 2, there's less energy because the datum is right at the bottom of the channel. So we have the flow depth, which is the same, and we've got the velocity head, which is the same, but the H sub F distance is equal to the delta Z. So that's what we mean by steady uniform flow, is that the head loss is entirely explained by the elevation change. And as a result, those three slopes will be parallel. Now, Manning's equation is used to calculate the velocity of flow, and if we know the cross-sectional geometry, we can find the flow rate by just multiplying the average velocity by the cross-sectional area. Manning's equation comes from what was previously the Chezy equation, where they said that the velocity was related to some roughness factor, the hydraulic radius, and slope to the 1/2 power. But through a series of experiments, Manning showed that there was a better experimental fit if you use the hydraulic radius to the 2/3 power instead of to the 1/2 power. So it's kind of an evolved formula. And if you're ever in a situation where you have a table of roughness values that are in these Chezy terms, you can relate the Chezy C value and the Manning's N value with this formula that's on the screen there. So here in the SI units, you'll see that the velocity is the hydraulic radius to the 2/3 power, the slope to the 1/2 power divided by N. And so then what that means is if you want to find the flow rate that's going through a channel, then that would be the area times the velocity, which is going to be hydraulic radius to the 2/3 power, slope to the 1/2 power, divided by the N value. Now, we can combine inside the hydraulic radius. Inside the hydraulic radius, remember, the hydraulic radius is the area divided by the wetted perimeter. And so sometimes I and the textbook will combine the area that's in the hydraulic radius this way. So it's area to the 2/3, slope to the 1/2, and then wetted perimeter to the 2/3. And so if we have the area and combining this area to the 2/3 power, then what it becomes is area to the 5/3 power, slope to the 1/2 power, divided by n times p to the 2/3 power. So that's how you would find the flow rate. And so this is just an alternate way of expressing the Manning's equation if you want to know the flow rate instead of the flow velocity. Now, the units of length that go into this would be meters, slope is unitless, and n value is unitless. And so it's not a dimensionally homogeneous equation because what you're getting out of the left side of the equation, velocity as units of meters per second. And so it's not dimensionally homogeneous, and therefore you're going to have a different units correction factor if you use the traditional units. And so if you're using, for example, feet for length, and you want to have feet per second coming out of velocity, then you have to multiply what you get by 1.49 to get the units to work out. So that's an important distinction between the SI version and the British gravitational units for velocity. Here's a table of n values for different material types, and so the smoother a surface is, the lower the n value will be. So if you have a really smooth surface, the flow is going to be at a higher velocity than a rough surface. And you'll notice that a big n value down in the denominator is going to reduce the velocity, where a small n value is going to increase the flow velocity. So let's do a first example for a rectangular channel, and it has a 1% slope. What would be the flow capacity for that channel if it was 1 meter by 3 meters? And so what we're saying is that it's 3 meters wide, rectangular, 1 meter deep. And so we want to know what's the flow rate if it's laid out at 1% slope. And so S is going to be 0.01. The n value for smooth concrete, if we go to the range of concrete, it goes from 0.01 for a smooth finish up to 0.02 for a rough finish. And so let's use 0.011 for the n value. And so hydraulic radius is area divided by the wetted perimeter for this rectangular channel. And so the area, you can see, is going to be 3 meters by 1 meter. So it's 3 meters squared. The wetted perimeter is going to be 1 on the right side plus 3 plus 1 on the left side. So the wetted perimeter is 5 meters. So if we want to know the flow capacity, we can substitute it into this equation. Area to the 5/3 power, slope to the 1/2, n, and then p to the 2/3 power. And so the area is 3 meters squared. Take that to the 5/3 power. The slope is 0.01 to the 1/2 power. The n value 0.011. And then the wetted perimeter is 5 meters, and we take that to the 2/3 power. So can you do the calculations there and find out what flow rate in cubic meters per second we should expect to see through this channel? Did you get 19.4 cubic meters per second?
$19.4, you said?
Yeah?
Yep.
All right. So 19.4 cubic meters per second. So that's the flow rate we'd expect to see if you have a measured depth of 1 meter of depth in a rectangular channel that's 3 meters wide, and it's laid out at a 1% slope, and it's concrete. So that's the flow capacity. Now the next part of this question is it's saying for a depth of 1 meter, what channel width would you need to convey a flow rate of 30 cubic meters per second? So now what we're solving for is we're solving for the width B in a rectangular channel. So let me erase all of this. Okay, so we're saying we don't know how wide the channel needs to be. What we're trying to do is we're trying to convey a flow rate of 30 cubic meters per second. The n value is still 0.011. The slope is still 0.01 for 1%. And so we have Q is area times area divided by wetted perimeter to the 2/3 power, slope to the 1/2 power, and dividing by n. So this is Manning's equation where I haven't combined the areas this time. So the area is going to be, if the typical variable that we use for the bottom width is lowercase b. So the area is going to be 1 meter high by b meters wide. So we'll just call that b. And then the wetted perimeter in this example is going to be 1 meter on the right, 1 meter on the left, and so it is 2 plus b is the wetted perimeter. So if we substitute all of that into here, what we're saying is we want to know for a flow rate of 30 cubic meters per second, the area is going to be b divided by 2 plus b to the 2/3 power. The slope is 0.01 to the 1/2 power, and then the n value was 0.011. So how good are you at putting equations into your Casio and solving for the unknown? That's the question. Pretty solid? Prove it. All right, solve for B. What we're trying to do is find the width that's required to make it so that when you send 30 cubic meters down this channel, the depth doesn't go above 1 meter of depth. So we want a maximum depth of 1 meter. So how wide does the channel need to be?
Dr. Wade, help. I don't know how to escape on a Casio. Help.
Sorry, I'm an HP guy.
No, somebody help. I'm stuck in matrix mode.
And it literally took 12 minutes.
Really?
It took me a solid like 30 seconds for Dylan. 4.26.
You have the same calculator, please help me stop it.
So you're gonna do 30, and you're gonna do calculate to get this done. Okay.
Okay, so if you want to solve it on Excel rather than on the Casio or other equation solver, then what you do is you just put in all of the values you know for the slope, n value, depth. Now you have to start with the guess value of the width, because what we're doing is we know that the flow rate is supposed to be 30. So this is solving Manning's equation based on the width. And so we'll do a goal seek where our goal is for the flow rate to be equal to 30 by changing the width.
How do you get it to show up as the fraction instead of like a 1?
All right, so what that says is that the width should be 4.26 meters. Anybody else get 4.26 meters? Yeah, thumbs up. Okay. So that's Manning's equation. Now what you just did was for a rectangular channel. Solving Manning's equation for a trapezoidal channel is a little tricky. So there's a video that I'll show you a little bit later that shows how you can do that on the Casio. Any questions about either of these examples before we move on? All right, so this is a table of Manning's n values. The one in your textbook, table 11.1, has it for a variety of different material types, both natural materials and engineered materials. There's a formula that you can compare the Manning's n value to the median grain diameter of the bed material. So, for example, if you have rocks at the bottom of a stream and you know the median diameter of the rock in feet, then you could estimate the n value from the diameter of that rock. And so the bigger rock is going to have you end up with a higher n value. We won't go through this example. It's just plugging the numbers into the equation, but I did want to show that there is an empirical way to estimate the n value if you go do physical measurements in the field. But usually, actually, what people would do is there's a bunch of pictures where you'd compare, you'd look at a channel, and you'd usually it's kind of an art assigning the n value. It's more of an art than a science having the right n value for a material. It's the sort of thing that an experienced engineer who's gone out in the field a lot of times is going to be able to look at it and know, oh yeah, we should use a 0.025, but if there's more weeds, we would have increased the n value. There are some imprecisions in assigning the n values. All right, so like I was just mentioning, trapezoidal geometry makes Manning's equation a little bit more tricky because oftentimes we're going to be solving for some unknown depth, but if the depth is unknown, then because the side slopes are tapered, it makes the area and the wetted perimeter difficult to calculate. If we go back to the formula for area and wetted perimeter of a trapezoidal channel, so the wetted perimeter is a function of the depth, but also this W function. The area is a function of the width, the depth, and the side slopes. So let's pause for a moment and look at this video that shows how, if you have a trapezoidal geometry, you can use your equation solver on the Casio. This is a video. So we've got this channel, and we are going to pass through there a flow rate of 175 cubic meters per second. So I'll put Q, cubic meters per second, is 175. And the bottom width of the channel is 15 meters. The N value, the roughness as it's described in the problem statement, is 0.013. The slope of it is 0.0045. And the side slope is 2. Okay, so the first thing we have to calculate is this factor W. And let me go back to the geometric parameters here. So you can see that W is 1 plus t squared to the 1/2 power. So equals 1 plus t squared to the power of 0.5. Okay, so we've got W, and now what we're going to do is we're going to solve for the flow depth by rearranging Manning's equation. Here's Manning's equation to solve for flow rate. If we put all of the known factors on the right-hand side of the equation, so we know the flow rate, the N value, and the slope, and then the unknown term on the left-hand side, because the unknown is the flow depth. And so I'm just rearranging Manning's equation like that. And I'm going to have a guess value of the flow depth. And so this is initially a guess, but then I'm going to use goal seek and iteration to find out the true value. So I'll just say initially a guess. Let's say maybe the flow depth needs to be 1 for that flow rate. So we're putting 175 cubic meters per second. Now, the left-hand side of the equation is going to be the area times the hydraulic radius to the 2/3 power. And so I guess what we could do is calculate the area and the hydraulic radius individually based on these parameters. So let's get the geometric parameters for the trapezoidal channel. Here it is. All right. So for the trapezoidal channel, the area, so the area in square meters is going to be B plus T times Y, and Y initially is just a guess, multiplied by Y. So that's the area. And then the wetted perimeter in terms of meters is going to be B plus 2 times Y times W. Okay, so it is B plus 2 times Y times W. Okay. So the left-hand side of the equation is going to be the area multiplied by, the hydraulic radius is the last thing that we need. So hydraulic radius is the area divided by the wetted perimeter. All right. So the left-hand side of the equation is the area multiplied by the hydraulic radius to the power of 2/3. Now the right-hand side of the equation is going to be N times Q divided by the slope to the power of 1/2. So the square root of the slope. You know, right now they don't equal each other. And they'll equal each other when we have the correct value for the depth. And so what we're looking for is we're looking for the difference between the two to be 0. And right now it's not yet 0. So if we say, well, what about a flow depth of 1.1 meters? That's getting us closer to a difference of 0. So what about the flow depth of 1.2 meters, 1.3? It's getting closer and closer to the correct difference. And so now we can iterate by changing the flow rate. So data, what if analysis, goal seek, and our objective is that we want to set this difference to 0 by changing the flow depth. And this is essentially what your calculator was doing, where he was saying it takes 20 seconds for it to go through and find the depth. It's starting with some guess value. And so now we're saying go ahead and change the flow depth until the difference is 0. And that tells us that the depth should be 1.573 meters. And so the initial question was, for a flow rate of 175 cubic meters per second, a slope of 0.45%, and this roughness value of 0.013, what would be the depth? And the depth would be 1.57 meters. So we're out of time for today. My suggestion is that watch that video and solve this same example using your calculator. Make sure that you're able to get that flow depth. It's going to be important to have that ability to do it. So I'll send you the link to the YouTube video so you can watch it separately, and I'll see you on Wednesday.